Dear participants, welcome back. We are in the last session of our FDP. That was supposed to be session 2 of day 1, but I have typically kept that banner as such it is, because we are rescheduling it. That day we had AICT innovation program. So this session, which was scheduled on Monday, September 21, as a day 1 session 2, which was scheduled at 11:45 a.m. We are taking it now as day 5, last session 3 at 2 p.m. It should be governed by one of the professor of our institute, Dr. Bora. She is professor of electronics engineering in the Department of Electronics Engineering, and she will be delivering her session on segmentation techniques in mammograms for computer-aided diagnosis. I will quickly take you through her achievements and biodata. She is PhD in Electronics and Communication Engineering from VNIT Nagpur. She is in charge of our BETIC Center, which is Biomedical Engineering Technology Innovation Center, in collaboration with BETIC IIT Bombay. She has experience of around 18 plus years. She was ex-chairman of Board of Studies of ENTC and Electronics Board of Studies of our institute. She is a member of ISTE, vice member of ISTE, senior member of IEEE, and fellow member of IETE. He has attended HTTP seminars and workshops and conferences. He has delivered so far 5 guest lectures, and as far as her publications and citations are concerned, he has 9 international publications in journals, in conferences 7. He has a Google citation of around 142 with H index of 4, ITN index of 0.3, and she has so far filed 6 patents to her credit. With all modesty, I welcome Professor Bora for her session for this 1-week online mode faculty development program on design trends and applications in biomedical and image processes. Madam, we have around 200 participants for this online mode FDP across the country, who are attending this FDP. They are faculty members of across our country of various engineering institutes in the form of engineering colleges and polytechnics. Once again, I welcome you and I request you to start your session. Madam, we are making you presenter. I would like to appeal to all participants and would like to inform to all the participants that Professor Bora was not keeping well since many days, but she was very much interested to deliver this session. With her health issue at her hand, maybe there can be some issues with as far as her noise or her voice or something is concerned. I request all of you to kindly bear with herself and ourselves as such. And I salute her that in spite of her health at her end, she insisted and she accepted, and she is here to deliver her session on the topic which has been stated so far. Madam, hand it over to you.
Thank you so much, sir. Thank you so much.
And at any point of time, if you feel yourself uncomfortable, please convey us. We will end up the session as such.
Yes, sir.
Thank you very much, madam.
Thank you, sir.
You are presenter now?
Yes, sir. Good afternoon, all the participants and all faculty members. Today's topic is segmentation techniques and mammograms for computer-aided diagnosis. So, what is the need of this actually? So So the contents will be the domain of the proposed problem will be there, then specific problem area in the domain. Basically, domain area is nothing but the breast cancer mortality and the early detection. And why we want to go for the CAT system. Now the second is the specific problem area in this domain. So it's a need of spectral missile detection and the missile detection, which is a reference point in CAT system. Available methods, limitations and challenges, basic objective and C, then detection of the two reference landmarks, then performance evaluation, results, discussion and limitations of the proposed method with conclusion. Now, what is the domain of the proposed problem? So basically, the breast cancer is basically the most common cancer in women. It happens in men also, but in women it is the most common cancer. In rural areas, it's the second most common. And in every 4 minutes in India, one woman is diagnosed with this cancer, and in every 30 minutes, one woman dies. This is with statistics from the Onco. One estimate was there that in 2012, it was the highest in the world actually in that year. 70,218 women died because of breast cancer. So now how the things are going. In US, 89% there is a survival rate for the post-treatment, and in India it is 60%. And the highest mortality in this due to breast cancer is because of lack of awareness and delay in the screening. And in India, it is detected normally in stage 3 and stage 4, and because they are detected in the later stages, so the survival rate is very low. So all these are the problems with the domain of the survey or domain of the proposed problem. So breast cancer is basically of two types: benign and malignant. Benign is localized at the site of the origin, and invasive it spreads. That is a malignant. So these are the actual issues. Few statistics are there from the WHO. Like as it was said that 70,000 women died in India in 2012, and that was the highest. So for that year throughout the world. So see here how that statistics is this. The incidence in India being compared 3 countries: India, US and China. This was the incidence rate. This was the mortality rate. Okay, and this was the prevalence, that is prediction for the 5 years. So in the United States, basically what happens, what the statistics indicate is that round off it will be 5 to 6. It means that every 5 or 6 women newly diagnosed with breast cancer, 1 woman will die. In China, it was like if 4 women are newly diagnosed, then 1 woman will die. But India in statistics was out of 2, 1 will die. So it's really alarming. So this is the ICMR report, Indian Council of Medical Research. So this report, ICMR report, from this it was mentioned that in 2020 that cervical cancer is declining because of the early diagnosis and all this. But breast cancer is increasing, is on the rise. So this is from India actually. So in many cities, the graph indicates it is increasing. Now, why the mortality is very high because of breast cancer? So it's because of patients turning in later stages, lack of awareness, shyness on the part of patients, social stigma is there, lack of basically diagnosis facilities are there, but in rural area there is no facility. So that's why the patient turns up in later stages. Cheap doctor-to-patient ratios and high treatment costs. So basic techniques for detection of cancer is basically mammography, sonography, MRI, CT, PET. But the golden truth, the confirmation is only from the histopathology, that is biopsy. So the effective techniques for the early detections are basically, now see why the effective technique is mammography, because there are the improved techniques are there, MRI, CT, PET are there, but the very difficult, it is out of reach of the majority of patients. So there is a broad gap actually. So this cancer burden is actually reaching the pandemic proportion. Okay, like in today's scenario, that COVID is pandemic, but cancer is also coming. Cancer burden is also reaching to the pandemic proportion. If cancer is detected in early stage, this is a very important one. If it is detected, it can give the very healthy life. If it is detected early stages, treated in early stages, definitely healthy life is there. Healthy life can be there. So mammography is currently the best and most cost-effective method for the early detection. When the cancer is at the early stage in the clinically impalpable situation. Impalpable means difficult to detect but via physical examination. So in that stage also mammography is the best diagnosis method in the early stage. So what are the challenges faced by the radiologist basically? Now, because of the structure of that radiographic structure of the breast, it's very difficult. Many times the abnormalities get embedded in the various densities of the breast tissue. And another issue is the positioning error and inappropriate mammography technique. Because in the mammography technique, positioning error can be there. Then false negative interpretation can be there because of the fatigue of the radiologist, because so many cases are there, so there may happen to false negative. Means if there is false negative means there is a cancer and it is detected as a non-cancerous. So this is very dangerous. So absence of serious and also in what happens, for the cases which are there, the previous study has actually what are the changes in the present mammography. So absence of previous imaging studies for the comparison. So because of this also the misinterpretation may happen. Now the solution to the early and accurate detection is actually the double reading. Double reading means two readings. It actually gives highly double reading actually reduces the number of false negatives. That is up to 5 to 15%. It was mentioned in the reference of 4. Yes, double reading is very effective. If it is done, definitely the false negative will decrease. Since double reading is actually not always visible because of the financial issues are there. So can it be like this? Can radiologists have the opportunity to improve their diagnosis with the help of the CAD system? That is computer-aided diagnosis, which is as an assistive device to the radiologist as a second reader. As a double reading as a second reader, it can suggest. It can give the radiologist that yes, you need to see more because this is the area where there can be a cancer present. So the basically CAD system is nothing but the pattern recognition algorithms. So they are aligned in step by step, and basically the CAD systems are they are used as a second expert to prompt the radiologist to the suspicious area. Actually, it gives a prompt. Yes, it will color that area and with a prompt. Yeah, this area is where there can be a cancer. So the second reading will check. So this advice will help the radiologist and will increase the actually confidence level of the radiologist. Yes, the false negative can be avoided. So this is basically computer-aided detection, that is computer-aided diagnosis. So the flow is the income mammogram will be there. Automatically the artifacts will be removed. Artifacts I will come to this point in the next slide. Orientation issue is also there and orientation correction needs to be done. So next is detection of spectral masses and the nipple location. Then segmentation of the masses is there. From that segmented masses, features are extracted, they are reduced, so the important features are then calculated and then they are given to the classifier. And then classifier will classify as benign or a malignant. And third point can be there as a normal also. So presence of CAD. Basically in US, out of 4, in 3 radiology centers, the CAD is present. So that over there, the radiologist takes the second advice from the computer-aided diagnosis. So that actually increase the sensitivity and specificity of the radiologist basically. The false negative won't be there. In India, the ratio is 1:100 and that too in urban areas only. So in India, the CAD systems, they are not actually used. If they are used, definitely the breast cancer will be detected in early stages and can give the best life. So the few available CAD systems these are the available CAD systems which are used in Europe and USA. Few of them are FDA approved, but few of them are like CE is there. Like they can be used in through other region of Europe. CE standard is there. So the need of the CAD basically, the need is that definitely it is going to help the radiologist as a second reader, and that actually will help in the final decision. Okay, and with this it reduces the workload of the radiologist and improves the accuracy in interpreting the mammograms. This was given in reference 1, and assisting the radiologist to minimize the observation lapses. And how it is done? By suggesting the areas on the original mammogram. Yes, you need to do the further analysis of this area. Something is there, some problem, like basically the cancer, it actually changes the architecture of the breast tissues. Actually, it changes. So wherever what happened by the normal radiologist, it may get actually unobserved. It may get unobserved. That architectural distortion may not get highlighted by the radiologist. But the CAS system mentioned this. Suggest this area here. These are the areas where you need to do the further analysis. So it improves the performance and the confidence of the radiologist. So databases which I had taken was that was a scan Minimas database that is available on the website on the Google, and this is from the local hospital, that is from CR images. These are the digital images. This is the scanned film images which are present on the website. So these are the spatial resolution, pixel resolution, and all these are the specification of the database, and the platform was MATLAB 16. Sorry. The standard views of the breast. There are two views actually, MLO and CC. MLO is what? Mediolateral oblique. So this is from the side position, view from the side, and this is from the top. So this is a CC view. Okay, head down, it say that. So this is from Minimas database, and this is from the CR database, that is from the local hospital. Now the regions of the mammogram. I am audible. Chitarna is here?
Yes, ma'am.
Okay. So these are the region of the mammogram. So this is the original mammogram, and in this mammogram, this is the pectoral muscle. This is the pectoral muscle actually, and these are the tissues. They are the dense tissues, and these are the fatty tissues. This area is the fatty tissue. Okay. So there are basically three types of mammogram: fatty glandular, and dense glandular. So these are the three types. This is fatty glandular, and this. Now the first, the specified problem area in the domain. So this is the first one. Now what is the need of spectral muscle detection? This spectral muscle. Why it is required in CAD system to detect this spectral muscle? And we do segment this spectral muscle. Segment is remove. Want to remove this pectoral muscle from the in CAD system. Okay, because see, the radiologists actually after seeing they are able to see that this is the pectoral muscle. But through the algorithm we need to detect this muscle, and then we need to segment out this, so that for the further analysis of the muscles, it is very much important. Like here, we discuss that. First point, why it is important? Because see, in CAD system basically, there are many. In CAD system, the first point is the breast tissue density is actually quantified there. Now, in automated means in CAD system, wherever this breast tissue density is calculated, in that what happens if the pectoral muscle is not completely segmented, then what happens? There can be the two possibilities: overestimation and underestimation. Okay, now how it is? See, for example, if the mammogram is of fatty type, there are tissues are less. Then in that case, what happens? If it is not removed, then that pectoral muscle, this pectoral muscle, like this is so fatty. So in this case, this pectoral muscle and this tissue, this will overestimate the density, overestimate the scale. In automated breast density quantification, the pectoral muscle must be removed, excluded. Otherwise, in case of fatty tissues, fatty means this, where the white tissue is less, it's a fatty tissue. In that case, what happens? It will cause a overestimation of the density. How it will cause? Because if that pectoral muscle is not removed, then it will add it to the tissue. Actually, the density, this tissue density is always less in fatty tissues. If fatty muscle is not removed, then it will get added. This is called as overestimation. And it is on the contrary, if, for example, in dense mammogram, what happens? If this triangular pectoral region will, what it will do? It will get mixed with the dense tissues and the muscle. Muscle is also dense. See, muscle is always white. See this also, and the tissues are also white. So what happens? It will underestimate the breast density. So this was given by Shah in this reference second. Yes, these are the issues actually, and that's why we need to remove the pectoral muscle. So the second point is, due to similarity between the pectoral muscle and the glandular parenchyma, what happens? High number of false positive occurs. False positive means there is no cancer, but it is detected as a cancer. So false positive occurs in mass detection. So that's why it's very important to remove the pectoral muscle in the CAD system. So these are actually the performance of some well-known methods. So this is actually this is the already existing work. Now, this is existing work. This is what? Existing work and their methods. Now, what are basically from all this, what are actually the challenges and where is the gap? Where we need to do work. So the problem is overlapping of muscles by the glandular tissues. Then there are the artifacts such as CT tapes and auxiliary folds are there. Positioning is an error. Then there can be the muscle. It can be straight, concave or convex, or it will be a mixture of both. So what happens? The existing methods are unable to segment this type of muscles efficiently. So there we need to work actually. And that's why we have designed the algorithm. The second specific problem area in the domain is what is the need of nipple detection? I will call this as a reference detection now. So this reference location is one of the significant landmarks for the comparing the asymmetry between the left and right, because this is a landmark actually, this is the reference point. So with that the asymmetry is calculated. Because asymmetry is there, then too there is a possibility of cancer. So this is the radiologist observe this. So in CAD system it's very important to detect the reference point. So radiologists normally pay more attention to this reference during the examination, as cancer can arise in the glandular tissues which converge onto the reference point. So this was given by this reference. And the coordinates of the reference are important in finding the architectural distortions. So all the architectural distortions, they are calculated from this with respect to this reference point as given in the Ranjan ATAL 15th reference. So these are the existing solutions. They had worked on this number of images. These are the authors, and these are summary of their work. So where is the challenge now? Where is the gap? So gap is invisibility of the nipple in mammogram, variation in the image quality, and patient positioning actually also creates a problem in this reference point detection in CAD system. So there's where we need to actually work. So the objective is basically to detect the pectoral muscle and the nipple in mammogram for CAD system by the heuristic approach. Now, what is heuristic approach? Like, see, in pectoral muscle detection, what happens for heuristic approach means, suppose for example, we are the radiologist, and we are very easily able to see that, yes, this is the pectoral muscle. Okay, so we can identify this. But so automatically, if you want to detect this, then there we need to apply the algorithm. So for that algorithm is by the heuristic approach, like seeing this difference, this is a straight line. This how we can have the algorithm which will automatically detect this area and will remove this. So I'm going to explain how that algorithm was developed. So first is the artifact removal. This is the orientation correction. So this is very important, because why this is important? Orientation correction. The orientation means what? In some mammograms will be oriented like this. Okay, the muscle will be on the right side. In some it will be on the left side. There will be a tag. These are the labels. There can be so many artifacts will be there. But in CAD system, we need to remove all these artifacts. We need to correct the orientation also. Some reference standard will be there. That will be always done on the mammogram before the segmentation part starts. Okay. So these are what the artifacts removal and orientation. So what is the need actually? So as artifacts are basically of high density. Like here, this label is of high density. If it is not removed, this will also get segmented with the help of mass. So it will cause error. In density and quantification, it will cause error. So we need to do this. High density, so it will cause a positive estimation. So that's why it's very important to remove the artifact. So for the bilateral comparison, for the temporal or bilateral of mammogram image, what happens? If the orientation of the breast in each image is kept same, right? For example, left and right, if the orientation is kept same, then it will be very easy to do the bilateral comparison. That's why orientation is important. Then correct orientation knowledge basically helps in detection of spectral muscle in MLO view, because in MLO only the spectral muscle is there. In CC view, just a head, CC is a top view. In that there won't be spectral muscle, but in the side view, that is MLO view, spectral muscle will be there. Okay, so the muscles are basically so by heuristic approach, basically, what is that? We had done this by the orientation. To correct the orientation, we had applied the heuristic approach, which was from the reference 18. This work was done by us. So this was the correction of orientation. And hence, each mammogram had the pectoral muscle in the top left corner before the muscle and nipple detection algorithm is applied. So this was given in many papers that you do this orientation and always keep in CAT system your mammogram on the same orientation. So this we had done. So I will come to that see this part. So this is that orientation correction. So how it is done? See, this is the way it is read, and as a table run this, I will show you how that correction was done. Able to see this MATLAB? Sir?
Yes, madam. Yes, ma'am. This is it.
Okay. So here let's read this image, Minimia's database, image number 7. So this orientation was right side. And then the orientation correction was applied in CAT system, and that's how that algorithm, mammogram, which was initially was right side, it was completely corrected and shifted to the left corner so that the muscle should always be in the top left corner, always. Whenever we give to an image to the CAT system, first the correction will be done, all the artifacts will be removed, and the input mammogram will be corrected in every sense, like the muscle will be on the left corner. So this we actually need to do for the CAT system. Without that, your CAT won't get efficient actually. It won't be efficient because you cannot always work with a mammogram which is right oriented, left oriented. So that's why it's very important. So here it is given that the original orientation was right and it was corrected, and it was left, it was flipped, and then it was shifted to the left top corner of the image. So this was the algorithm how which we had done. No audio. Except just a minute. It was written there. No audio. I'm audible.
Yes, ma'am. You are audible. I have replied to that. Archana ma'am's reply is that.
Now she is okay, na?
Yeah.
So this correction we had done for the mammogram. First, in CAT system, this is very much required. We had discussed that in the block diagram. So this correction was done here, and each mammogram had the pectoral muscle in the top left corner before the further segmentation is applied. Okay. Then enhancement was done by the Clahe method, CLHAE. This is the contrast limited. It's a localized method which works for the histogram equalization. So the approach is heuristic approach to detect the pectoral muscle. So how that was developed here, I will describe the algorithm, how we had developed this algorithm, just by the approach that how the radiologist observed this pectoral muscle, and that we had included that logic in the algorithm. So see here, what we have done, this is the mammogram. Okay, this is enhanced mammogram by Clahe method, and then what we had done, we calculated the local entropy in 9x9 neighborhood. That was the one feature. Second feature was the Sobel operator that was applied to this image to calculate the gradient orientation angle. So we had applied the Sobel to this, and at every point we obtained the gradient orientation angle. Okay, that was the second feature. And then what we had done, we had developed one texture plot of the mammogram. Like this is the original mammogram. Instead of working on this original mammogram, we had developed this plot. This third is the textured plot of mammogram, which will be called as TPM. Now, what is the CPM? How this was calculated? So it was like this. It will be 1 for this criteria. Like HXY is nothing but the entropy, and HT is the threshold. So this threshold was calculated from the local value. So like 50% of the threshold value. Okay, so this HXY, wherever it is greater than the 50% of the local number, 9 cross 9, 9 cross 9 is the local area, and from that, whatever the mean value of in that 9 by 9, those pixels having the entropy greater than the 50% will be considered as first point, first feature, and for the Sobel operator, the gradient angle, which is for the angle 30 degree to greater than 30 and less than 90, for all the such pixels, and for the IXY means the intensity of every pixel point greater than 0.5 of maximum. For all this set, all the value will be 1 in TPM. So this are the all values in the TPM where this criteria is satisfied, and that's why it is called as textured plot of mammogram. So instead of working on the original mammogram, we have developed this textured plot, and then on this mammogram we had applied the Huff transform. Huff transform, it indicates the straight line actually. Huff transform. This is given in the Gonzalez also and AKGN also. So we had applied the Huff transform algorithm, and then it will detect the straight line. So this straight line was detected with the help of Huff transform, which was applied to this TPM. So this is straight line, and this straight line was just overlapped on the original mammogram. That's it. So first point was to detect the straight line. Now to estimate the correct spectral muscle, it is very important to further this, improvise this. So what we have done, we applied this again the next logic. Yes. Now on this straight line, we had applied this algorithm, that is distance surround separation technique we had applied. So what is this distance surround separation technique? I will explain with all these steps. Before that, I will first explain you with the help of diagram how we had done. Now, see, the straight line was detected. The straight line was detected. Fine. Now, from the straight line, we had considered the, for example, 30 pixels on the left side and 30 pixels on the right side. The two straight lines just in parallel to the Huff transform line. Okay, this is shown here. This is the two lines which we have considered. So for example, this PX, for example, 30 pixels. I had done this empirically, and I found that because PX equals to 30, I was getting almost for every image the best segmentation result. So this PX is nothing but from the straight line. Here the 50 pixels I had moved here. So this is a straight line which is 30 pixels inside and 30 pixels outside. Okay. Now from this, what the next point is here. This is this selected. This is called as now this region A, B, C, D. This region is called as what? Selected texture plot of mammogram. That is STPM. Just this was selected from the initial image. Just don't consider this area. Just work on this area because somewhere your exact muscle will be in this region only. Okay. So now the next point, what we have done after this, getting this, we have done what? We have done 5x5 block average STPM. In this image, in the 5x5, we had applied the block averaging. Averaging means what? In 5x5 matrix, whatever the values of the pixels was there, we had averaged them, and what we have done this year. This is what average. See, now this is not pixels. There are 5x5 block average STPM. Okay. So this was done. Why it was done? Because see, in this there are very cluttered data there, point. So instead of that, we have done the region where really there is the high intensities there. So we had averaged this. Now, while doing this, STPM, I hope it is clear. It is the nth and block average. So that what happens, the pixels which are least involved in the spectral edge representations are removed. So we have removed the actually the least possibility. We have removed that. And then we have considered this average STPM is what is the block averaging. See this. What we have done, ROI, that is STPM, we have done this, and we have averaged them. Okay? Now the blocks with average value of 0.51 are kept as 1 and else they are made 0. Okay? After doing this, what happens? We had obtained this area. Yes, this region we had obtained here. This region we had obtained here. Okay, this region. Now the next is what? This distance around separation technique is what? From the right corner. We have calculated the first intensity 1. This is what it is calculated from the right side. So this right side we have calculated this. So this is the horizontal distance from the right edge. We have calculated this. Because this is a heuristic approach. We have developed this based on what actually radiologists do. So that we have developed as an algorithm, and then this was calculated here. So this was horizontal distance from the right edge. This we had calculated. And then what we have done, how the C part is developed? This is developed like this. After averaging this, what we have done, we have calculated the string of pixels position SC. SC is the string of pixels, okay, is obtained and considered as a rough spectral edge as shown in this here. As a rough spectral edge. Now this red line is the set of SP. How it is obtained? These are the first points. These are the SP, this horizontal distance from the right edge. Wherever we are getting this horizontal distance from the right edge, we have built that as a set SP. Here. Okay, this is the binary average STPM. Images scanned horizontally from the right vertical edge to pick the first non-zero pixel. From the, this is actually in 70. See here what I had explained this. In 70, this is what first non-zero pixels were extracted, and they are nothing but the set SP. And this red line is what? The actually estimated muscle. But see here, there are many outliers are there, like ye wala jo point, this point, they are called as outliers. Why they are called as outliers? Because they are not from the spectral muscle. They are outliers. So for that we need to actually improvise it. How we have done this? See, a string of spectral SP is obtained, and see here. Now the next logic is the outliers in the SP in this red line. These are outliers in the SP. This is a set of pixels which are nothing but this horizontal distance from the right. The first non-zero pixels, all these points, locations gives you a set SP, and when we plot this graph, the red line goes like this. In this, the outliers are there, so we need to remove this outlier. So we have applied the logic, and that works very beautifully. So here, what we have done, we have obtained here what? The distance, the horizontal distance between the point on PQ and SP. What does it mean? This is your PQ line, blue line is your PQ line. Fine. And your SP set, these are the pixels with your SP sets. We have obtained this distance, blue and red, this distance, SP distance. This distance, DSP. We have calculated this. Here, we have calculated this, DSP. This distance was calculated, fine. And then the empirical threshold to remove the outliers was applied. So, because they had calculated this. Okay. Now the distance which is very, very far away, which gives very large value, definitely will be the outlier. Now how to remove that all the outliers? And for that, the statistical analysis was done, and from there the threshold was developed, like median of DSC and IQR. This is interquartile range, which was calculated from the box plot basically. So it is nothing but the distance between the 25% and the 75% of the statistic. That is when we arrange it in the ascending order, that IQR is this range, IQR range, 25th to 75th. I hope this part you might be knowing. So as I will come to that point also. So this is here in this graph, how the outliers was calculated here. So this was the threshold. 3 point. This was the threshold. This is 30.92 was the threshold. And here, these all are the outliers. All the points which are above this. Above this means this is the distance. On y-axis, DSP is there. Okay, and these are here the number of pixels in XP. Okay, so those points which are above the thresholds, they are the outliers. Straight away they are the outliers and they are removed from the data set of SP. Okay, sorry, not data set, from the set SP. And this remaining will give the actual muscle, and this was this muscle. Okay, so this is called as the absolute distance plot between the pixels in SP and the horizontal distance between the straight edge. So this is what your x-axis and y-axis in this plot. Threshold was calculated and the outliers were removed, and this smooth spectral muscle was drawn here with the help of the polynomial, cubical polynomial, after removing the outliers. So this is how the distance around separation technique, heuristic approach was heuristic approach was developed to detect the muscle. Okay, so this is now the heuristic approach for the nipple detection, that is for reference detection. Here we had used the radon transform. So in radon, what we have done, we have used the orthogonal pair. Orthogonal means the two radons which are 90 degrees. This is at 90 degrees. So this is applied to the mammogram to detect the reference point. This is a heuristical approach. Totally based on the actual the mammograms, it was applied and it works very nicely. So it's supposed to automatically detect the reference point in the CAD system. So how it was developed? Using the slope of the muscle. Now from the pectoral muscle, we had already the straight half transform we had calculated, and from that half transform straight line, we obtained the slope of the muscle. So that slope was used here to generate the two orthogonal radon transforms to detect the reference point. Again, which is visible or invisible, it is able to detect actually. And that was the challenge which was there in the literature. If it is invisible, it is very difficult to detect the reference point. Okay, so the proposed method depends on the accurate detection of the straight approximation of spectral muscle. So definitely this distance around separation technique or the textured plot technique, this works very well. So this slope is very important. Straight line, this slope of this line, because based on the straight slope line, the next reference that radon transform is applied in the CAD system. So how it works here? For example, this is your MLO mammogram is there, and this is what the spectral muscle is there. For example, the slope is phi. Okay, so this phi. So what is done? The first radon transform is taken at the angle phi. Radon transform, I hope you might be knowing how the radon function is, how it is done. We need to select the angle. So the angle will be a phi. So this first radon is what this. So this is a radon projection at angle phi. Okay. So here we are getting the radon transform like this. It is the sum of all the intensities coming throughout the mammogram. Radon is basically sum of all the intensities which are coming at the angle of 5 degrees in this mammogram. So the pixel intensity plot for the radon is like this. Okay. So what from this plot, what we have detected, point A is detected. Okay. So the point A is detected. Point A means the last point of this intensity plot. Okay. Now the second mammogram, that is the orthogonal pair. The second orthogon was taken, radon transform is taken at angle phi plus 90 degrees. So this is the projection. So this is the projection which is taken. This is a sum. Add all the intensity that gives this value. So this is the sum of radon is nothing but sum of all the intensities coming in throughout the line at that angle. So this is what radon transform. So this is the second radon which is taken as phi, this phi plus 90 degrees. So this is the orthogonal pair. So this is the orthogonal pair, and from this radon transform, radon projection, what we are calculating the maximum point, the maximum intensity point. So this is your point B. Okay, and if we plot the two lines from point B and point A, and the intersection of these 2 points will give us the reference point location. So that again, this was a totally heuristic approach which we had applied to detect the reference point in CAD system. Okay, so this was done on the MLO view, and in CC there is no issue because in CC there is no pectoral muscle. So two radon transforms are taken at 0 degree and 90 degree. That's it, and that helps to detect the reference point in CC view. Okay, CC means here this is top view, this is side view, MLO view. Okay. Now, steps, I think I had explained this. These are the slope of the pectoral muscle, and from this slope, they have taken what? radon transform and locate the point A, and then from 5 plus 90 degree locate the point B, and draw these two lines. The intersection of line at A and B is the location of the reference point. So this is how it is applied. Okay, this is how it is applied. So this is what the mammogram. This is spectral muscle straight line detected by the Hawk transform on the texture plot, and this helps to give the slope, that is angle, this angle, and the two radon transforms were taken to indicate the point A and point B. And then here, this is the location of point A. This is the radon transform at angle 5. This is the location of point A. And then at 5 plus 90 degree, this radon transform was taken. This was the radon plot. And here the maximum highest intensity point was calculated, which indicates the location of point B. And then the two lines joining point A and point B. Here, see here. Two lines joining point A and point B gives us the location of the reference point. So how the performance was calculated for the muscle? It was with the help of 4 parameters. Basically, the 3 parameters, and 4th is the quantitative. That is PSI, Spectral Score Index, Hausdorff distance. Basically, it is the maximum of all the minimum distance between the 2 points. Now, what are the P and Q? P and Q are basically P is the acquired by the algorithm, by the proposed method, and Q is the standard spectral muscle, which is given by the radiologist. So, if you what this 2 locations. We have T also set of P pixels, a set of T and set of Q. And when we find out the distance, this is the Hausdorff distance. Maximum of all this minimum distances. Then is the false pixel percentage of false positive or false negative. And then the 4th is Spectral Score Index, which is quantified like accurate, adequate, and moderate, and inaccurate, and inadequate. The 4th is 1. Then, for the nipple detection, the performance metrics was such as goal distance. It is nothing but maximum of X minus C. Now, what is NM and NMR? NM is the automated by the proposed method, and NR is the radiologist annotated location. So, these are the 2 locations, like X, Y, and these are again the C, D. So, if you find out the distance, X minus C and X Y minus D, maximum of that is that we will use the telescope distance. And based on this, the algorithm was applied, like the index was calculated. So that is nipple score index, NSI. NSI is nothing but what? If the C distance is less than 5 mm, it is accurate. If it is C distance is from 5 to 10 mm, then acceptable, and above that, not acceptable. So these are the results of the Minimas database, and this is CR database for the muscle, and for MLO, it is a muscle detection. So red line, this is the muscle detection. This green is the reference point detection with the help of the proposed method. So these are the results. These are the comparisons I have done. Now, what are the limitations? There are definitely limitations are there for this heuristic approach. If the muscle is too small, then it's very difficult if this algorithm won't work properly. If there is a low contrast again, so it won't work. But actually today, in digital mammograms are there, so there is no issue in the contrast actually. But in a minimal database, this was the issue when the scan film mammograms were there initially before 30 years. Now there is a digital techniques are there, so the low contrast hardly is there, because in today's scenario, FFDM technique is there, full field mammogram technique is there. So these are the limitations. If small size is difficult. It may fail. For nipple detection method sometimes fails because the rolling over of the skin is there and the drift mammogram is there. So these are the limitations, and these are the conclusion is that overall the conclusion and the impact of this work is that this is a very simple heuristic method is there to detect or to segment the muscle and locate the vessel in the mammograms. They are very important for the radiologist, so they need to be done automatically in CAT system. So the results were 97% for the muscle and 92.67 for the reference nipple location. And the impact is that with a high accuracy, this method can be used in the CAT system. And I had used this in this CAT system. Here, these are the 2 results for the CAT system. Here, mammograms this is a GUI. Mammograms were loaded. Then artifacts were removed, then pectoral muscle was detected. Here, original mammogram, then it is it is corrected, and then it is shifted left here. See, and this is enhanced mammogram. Then here, the texture plot was obtained, then straight line was detected, and there is this is what you that outliers are there in the mammogram red, and then it is smoothened out, then muscle was segmented out, and then here the edge of the border is detected, and then the reference point is detected, and the mass is detected. So this is the GUI for the two images from the database. Okay. So acknowledgement to the Dr. Suchita ma'am. She has given us the database also and also given the ground truth results also. These are the references. Okay. Thank you. Any queries?
Yeah, Bora madam, thank you very much. I will take up, if there are any queries, I will read it out for you.
Okay, sir.
Okay. Let me go through it, if there are any queries. Yeah, dear participants, the session is over as such from Madam's end. If you have got any queries, please put it in the chat box or maybe in question answer. So that we can take up few of the questions. Madam, there is one question from Dr. Shah.
Sir.
Dear participants, mute from your side. Madam, there is one question. Can entire processing be done through MATLAB?
Yes. I had done through MATLAB. This can be done through Python also. Actually, but I had done through MATLAB. Okay. The UI was developed in the MATLAB.
Yeah, thank you, madam.
Yes, sir. Thank you, sir.
Another question is there, madam, from Professor Lakshmikant.
Yes.
What do you mean by heuristic approach?
Heuristic approach is the approach which actually by the practical way, just by observation, just by seeing what we see, just you try to implement that approach in your algorithm.
Okay.
Sir, please ask that. I am okay with that heuristic approach.
Yes, sir.
Ma'am, one more question is there in chat box. How you segmented the malignant area?
Malignant area that I segmented with the help of, actually that segmentation I had not covered yet, but the method was K-means, fuzzy K-means, and then rough K-means algorithm. So I had compared the three methods for the segmentation of the masses, actually where the tumor region is there, tumor. So for that, the K-means algorithm, fuzzy K-means, and rough K-means algorithms were applied, and for the further classification, two methods were applied. Neural network was applied, and then the HCM method was applied. Again, there is a hybrid combination again. Rough K-means was developed, rough neural network was developed to classify the segmented tumor region. Like it was here, see here, it was there in this. I will do this. Here, in this cat, here, this is a segmented region. So here the classification was like benign malignant. So this CAT system had given that this is a benign algorithm. How it is calculating by these features. These features were extracted, these features, and this with the base of this feature, and by training, it had given that yes, this segmented mass is benign. Like here, it was malignant. These are the segmented regions. These are the segmented features had mentioned, and by training, it had given that it is malignant. And it was pathology proven mammogram was this.
Next question is how to detect double layered pectoral muscle.
Double layer. So in double layer, for example, there is a double layer. I will come to that. Like here, see here, this is a double layer. Because of the positioning error, there is some layer there. Or it will happen that here also there will be two layers. Okay. So how the algorithm works? Basically, it calculates the distance from the right part. After correct orientation, definitely your muscle will be in the left corner. So that's why it's very important to first orient the input mammogram. First is very important. So after orienting properly, then it's very clear to the CAD system the muscle is in the left side, and then calculate the distance from the right side. For example, if it is double layer vertically or double layer horizontally, it will calculate the first pixel from the right side. To estimate the pixels which can be on the muscle, which can be. So if it is double layer, no issues, the layer will be on this side, but it will estimate this first layer, the layer which is from the right side. Okay, because the position it may happen, the layer can be vertical or horizontal. So there is no issue. This algorithm will detect the rightmost pixels, the first non-zero pixel from the right side. So it will estimate properly. I hope I have made it clear.
Ma'am, also in continuation with previous question and segment, how to detect double layer postural muscle and segment. And segment.
Yeah, this is the way. Only.
Okay.
So, for example, I will come to the result. For example, this can be double layer. There is a layer here. One time. Can you unmute that participant? Chaturmani sir, can you unmute?
Yes, I will say. Yes, ma'am. I have unmuted Mr. Pratap Vijay. Hello?
Hello.
Please. Yeah, I am able to listen.
Yeah. I have read one question about ground truth also.
Ground truth, okay.
Yeah. What was the basis actually used for the ground truth in breast cancer? Actually, for the standard database, they are providing ground truth. I think for MIS database they have provided. But for the radiological images, whatever we people are taking from clinical images from the hospital.
So in that case, doctors, like Suchitra Mehta ma'am, she has helped us a lot because she has just indicated that, this is the muscle region, what we see actually. What they observe, that is the ground truth. Okay? So I had marked that, with, for example, like how to calculate the false positive and false negative. So in that case, what my proposed algorithm had given is this. For example, like in this 3, I got the PSI at 3, means there is an error. Okay, so there was the error of 5 to 10%. So in this case, probably what happens, the muscle region, this region, the ground truth was this. This was also covered in the radiologist image, like a pectoral muscle. But the algorithm was not giving exactly the same. Because because of this tissue, because of this dense tissues, there is an overlap. So this algorithm, there is an error of 5 to 10%. That's why this is 3. But the radiology, the ground truth, that is the radiologist, had marked this as this part. This part is also covered in the radiology, the standard database, the ground truth result. So there was issue, and in this also the Rangan sir from the category, he had helped us a lot for giving us the ground truth images for the mini-MIAS database, because in pectoral muscle was not there in the mini-MIAS database, only this part. Wherever the malignancy is there, that point is located in the database actually, where the malignancy is there. So that's why. Yes, sir.
only malignant parts were given.
Yes, sir. So malignant part was there only mentioned. So in this case, for the spectral method also, because sir has done very, has compared his book also on the same database, meaning yeah. So I got the ground truth images from the Rangayan sir also.
Yeah. Rangayan Sharma.
Thank you, madam. Will you take one last question, madam?
Yes, sir.
It is on the WhatsApp group that faculty member has posted, participant has posted. Suggest some references for feature extraction in your case.
Feature extraction in my case. Okay. Actually, in this work, I have not mentioned the feature extraction, so it will be difficult for me to from this references because these are all the references for the two segmentation, that is two landmark points. So I will, if he or she is interested, I can give us the IEEE transactions few papers I have. I can share that paper, those papers. Because I have not explained the feature extraction method. So in references in this presentation, they won't be covered. They won't be taken because it is not discussed. So only this is a chat system I had included as a screenshot only to give the importance of this impact. Yes, these two methods can be used in the CAT to assess the radiology. So I can mention or I can share that.
Yes, madam. What we will do, we can request the participant, the particular participant who has put up this question, Mr. Hemant Kapali. He can contact you by mail or he can route his query through me. I will get back to you on this.
Yes,
Okay.
sir. I will share it to you or to that person also to the people.
Okay. Okay. So thank you very much, madam. Dear participants, that was Professor Bora's session. I hope she has taken you through all the things that are related with the topic she had done, that is segmentation technique in mammogram for computer-aided diagnosis. Madam, on behalf of all of us, we are very much thankful to you. Even though you were not in good health condition, you insisted and you made it a point that you deliver this session today. We are very thankful to you.
So thank you so much for giving us the opportunity. Thank you so much.
Thank you, madam.
Thank you, participants.
Take care, madam.
Yeah.
Well, dear participants, we have come to the end of our technical sessions as such. We will be soon starting our valedictory. Please give us some time. This is now, as of now, this is 3:05. Okay. So, we will be starting by 3:15 as such. Okay.